So like I just said, and what I'll say again for the podcast is, this is a level surface problem with a force applied at an angle. It just happens to be a vertical level surface, not a horizontal level surface. So what I'm going to do first is, now notice, you can't really see very well from the picture here, but the angle in the problem is given right here. Now, because they drew it's very shaded, but there is a line showing right there. So they're showing a line there, and then that's the force. So when they say 40 degrees, if they give you this, that means that the 40 degrees is actually right there in the picture. So it's up in that corner, because you need to know that, because I'm going to now take that force and break it into its two components. Another thing, the force that's showing as F on the picture, I'm going to just cross this out and just label it over here the way we label it, and we would label that as the applied force. Another thing, most of the time when I draw force vectors, I draw them so they originate on the object that's being affected by the forces, and they move away from it. This one is not doing that. It has the force ending where the object is. But I could have taken this arrow and moved it along that line and had it over here if I wanted. All right? Because it's a force happening on this object right here. And if I'm going to break up all my forces into their x and y directions, then this one I have to break into its components. So I'm going to take that applied force and break it into its x component, and I'm going to break it into its y component. So in labeling these, this is going to be my applied force x component, and the other side is going to be the applied force y component. Everyone follow that? Now, there are other forces that are acting on this block. Now, I know there's a part A and a part B, but I'll get to that in a second. The object has a mass, so it's going to have a weight. So the weight in this problem is going to be a down force, and I'll put it over here so it doesn't get in the way of my labeling of that side, but there's my weight. And I'll label it W. Another thing, notice that in this problem, they're giving me the weight in pounds. So if they're giving it to me in pounds, that means that this problem is going to be an English unit problem. So I'll write that in. So the weight is 20 pounds. Another thing given in the wording of the problem is that the coefficient of friction is 0.560 between the vertical wall and the block. So somewhere on this picture, I'm going to write mu equals 0.560. Any questions with what I have so far? Now, if that red arrow that's on my picture was the only force on the block in the x direction, then this block would be moving to the right. It's only going to be moving up or down, so what force would be in the opposite direction to keep that object from going left or right? The normal force. So the normal force is always a force perpendicular outward from the surface. Not perpendicular upward, but perpendicular outward. So since the surface is vertical, then the normal force is going to be horizontal. So that's going to be my normal force. And what I know is that this arrow and this arrow have to be the same length, because those are my only two forces in the x direction. They're going to balance each other out. Now, if you read the problem, there's a part A and a part B. Part A says, what minimum force is required to prevent the block from sliding down? So, to prevent the block from sliding down, friction will be up. Because if it moves at all, it's going to move down. So in order to move down, it has to overcome friction, which would oppose that motion. So for part A, my friction is going to be in this direction. So that's my friction. So I'm doing, you can make a separate picture, or you can just do it right on the picture if you were to have a picture. I'd rather than redraw the picture, I'm just putting them all right there on the picture that's already there. Any questions so far? Now, if I add up the applied force and the friction, those two arrows should equal the length of the weight. So if I take this and put it on the end of that, the length of that should be equal to the length of that, because we want to be right on the verge of, we want a minimum force. We want the smallest force that we can have just to keep it from sliding down the wall. So we basically make everything equal. It's hasn't slid, it's right there. It's right at that point that if I apply any less force than what I get for my answer here, it will start sliding down the wall. So if that's my picture, the next thing is I have to sum up my forces. So when I sum up my forces in the x direction, what's my equation going to be in this problem? Now this is a homework problem, so I should have some people that are shouting out the answer, right? What would if I sum up my forces in the x direction, what should I have? Yes. Well, usually we call to the right positive and to the left negative. So FAX minus FN. Now, again, it always equals MA, but we're not going to get any movement, any motion horizontally, so it's going to equal 0. So there's my equation in the x direction. Who can tell me what I should be writing when I sum up my forces in the y direction? Again, we're going to call up the positive direction and down the negative direction. Yes. Okay, and I'll put the FAY first because I just like to have my two components first. So FAY is correct, plus F, because both of those are up, minus W, and again, they would equal MA, but in this problem, we want to get it right when it's the minimum force required to prevent it from sliding down. So this is going to be 0. Okay, so we have this. So the next thing is, if I look at this and try and figure out what I don't know the applied force. If I don't know the applied force, then I can't get a value for FAX or FAY, so I'm going to write them in terms of FA and in terms of the trig function, the appropriate trig function. So I want to rewrite this first equation, and so if I look at my picture, now remember I told you the 40 degrees is right there. So FAX, it's going to be the hypotenuse times what trig function to get FAX? Is this side right here the opposite or the adjacent side? The opposite. So what am I going to have? Sine. So I'm going to take that top equation there, and I'm going to replace FAX with FA sine of the angle minus FN equals 0. So what can I solve for now? Well, what do I know from that equation that I just wrote down? If FA sine theta minus FN equals 0, then don't I know what FN is? So FN is what? Right there, what is it? FA sine of theta. All right, so I now have something that I could replace Fn with. Now, is there anything that I can solve in terms, again, I know this isn't a number, but we'll worry about that later. It's something that I've replaced Fn with. So is there something now that I can solve for? When we know Fn and we know mu, what can we solve for? Friction. So friction is going to equal mu Fn. So mu, I know what that is. I'm going to leave it as a variable. And Fn, I'm going to replace with Fa sine of theta. What I'm trying to do is I'm trying to reduce the number of unknown variables I have in this problem. So now, if I look at the second equation down here, I have something that I can replace friction with. I know what the value of W is, and I can also replace Fay. I haven't done that yet, but what will Fay equal? So let's get Fay in terms of Fa. So Fay is going to be what? Cosine, the hypotenuse times the cosine. So it's going to be Fa cosine of the angle. And if I take the second equation over here and plug things in, the only unknown variable I'm going to have is going to be Fa. Because Fay is going to be replaced with Fa cosine theta. All right, so that is this. Now plus F. So I'm going to put plus mu Fa sine of theta. So this has replaced that, and now minus W. So I'm going to move it to the other side and just set it equal to W. And at this point, the rest of the problem is an algebra problem. Because if you look, I do know, if I do a checklist here, I do know what the angle is, I do know mu, and I do know W. So the only variable that I don't know in that equation is Fa. And what do you do when the unknown is in more than one term? Factor it out. So I'm going to do two steps at once here. So if I were to factor out the Fa, what I would have in parentheses will now be what I'll have in parentheses will now be down in the denominator when I move it to the other side. So Fa is going to be W divided by the cosine of theta plus mu sine of theta. And I know all those numbers, so as long as you know how to use your calculator, you can get the answer. Now, I want to say something about this because notice I didn't plug in any numbers earlier. I wasn't able to, but the reason why you deal with variables is now, if you remember in Part B it says, what's the minimum force needed to start the block moving up the wall? Well, if I want to move it up the wall, the only thing that's going to change on my picture is if I want it to be right on the verge of going up the wall, then friction instead of up would be down. Which means I have to push harder with that force to get enough of this to overcome not only the weight, but the friction that would be opposing that motion. So the only thing that changes, and I'll do this in green, and I'm running out of time, so I better be quick. Instead of plus F, it would be minus F for Part B. And if that's minus F, then that's minus right there, and that's minus right there. So the only difference between Part A and Part B is just changing the sign of my friction, and I don't have to redo the whole problem again. That's the only thing that's going to change. So like I said, in Part A, friction will be in that direction because you're just trying to keep it from moving down the wall. But then when you want to get it on the verge of going up, it would have to overcome friction, which again would oppose the motion and would be down.